Welcome back, everybody. So we're going to continue talking about energy here. And the thing that I would like to focus on, now that we have a whole bunch of different kinds of energy up here, is how we're going to solve problems using energy as a strategy. And the kind of fundamental way that we are going to do this is by using this thing here, which is the work energy theorem, which you might know by a name called conservation of energy. This is kind of a more colloquial, fast and loose term for what we are going to be talking about here. And the reason for that is often, but not always, we like to pick a system such that the net work done by external forces is zero. And when we do that, then we put a zero over here and we look and say, oh, look, the change in energy, total energy of our system is zero. We might say there that it is conserved, right? So that's kind of why this is sometimes called conservation energy. Kind of how you use this strategy is number one, strongly think about what the energy of your system depends on. The things that we have talked about so far is where objects are located relative to each other. That's potential energy, right? Something is closer or farther from the Earth, or a spring has changed its configuration. Those are all changes in position and location that give you potential energy changes, or on how fast something is moving, right? If you change how fast something is moving, that's going to change its kinetic energy. And another thing to remember here is it's always changes in energy that we are going to calculate. You can't necessarily say very easily, or even at all, like the total energy of this thing is 27 joules. Right? It's just there's so many different kinds of energy, and it doesn't matter where you say zero is, that an absolute number for energy just doesn't make sense. What makes sense is here's how the energy changed from this state to this one. Once you know that that is what you want to do, you have to make sure to choose your system and really carefully say what is in my system that can change energy, and what is out of my system that can cause a change in the total energy of that system. You want to make sure to identify all the different forms of energy that are going to change in your system. You can draw some energy bar diagrams like you saw in the simulation a few moments ago. And you want to make sure that you can identify all the energy symbolically so that we can start manipulating them and solving for things. So that is kind of the different things that we want to do. I'm going to do a little practice problem here. I'm just going to make one up. I'm going to think about a task where I've got maybe a hill, and I know this is a bet here. Wait, I can draw better. Zoom will let me draw a straight line. Here we go. So I'm going to think about a hill that has some angle theta here, and I'll draw a little picture of me. This is stick figure me, and I am tasked with stopping a big boulder from rolling down the hill. So this large boulder has started rolling down the hill, and it gets to me, and I'm like, oh no, there's important stuff over here, treasure or something, and I don't want the big boulder to crash into the treasure, so I'm going to try to push against the boulder and stop it. I personally would not be very successful at this, but we'll go ahead and see what might happen here. So I'm going to go ahead and try to follow these different steps that we have here. I'll kind of flash back over here. So I want to choose a system, identify all the forms of energy, draw some diagrams, and then identify all the energy symbols. So my goal here is I want to stop the boulder. So at the end of the day, I need to get down here to the bottom of the ramp and have the boulder not be moving. There's basically no way that I'm going to be able to solve this problem without putting the boulder in my system, right? So system, boulder. But I can put other things in my system. And I'm going to choose, like we often will in this class, to put the Earth in my system. Because I know from what we talked about last week that once I put the Earth in my system, I can talk about a change in gravitational energy. So that lets me go down here and start thinking about forms of energy here. I know I'm going to have kinetic energy. And now that I've put the Earth in my system, I can talk about gravitational potential energy. All right. I know that I could decide to put me in the system, but I want to not do that because I expect that I'm going to do some work on this boulder. And I don't quite know how to account for the change in potential energy in like my cells as I push on. So I'm going to leave myself out of the system. When I do that, let's me make sure I'm following all the steps here. So I've chosen a system. I've identified the forms of energy that I'm expecting to change in the system. I can draw some energy bar diagram. So I'm going to think about this as a before and after, right? So before and after. Whoops, that's weird. Zoom has never done that before. All right. So in the before situation, I want to think about what kinds of energy I've got. So I'm going to draw a little bar diagram here, kind of split between the before and after. I've already identified the kinds of energy that I've got here. So I'm going to go ahead and put K and U. And then over here, I will put a K and I'll put a U. And again, this is gravitational potential energy, and it's the kinetic energy of the boulder. Let's see. I think blue is a good color for energy bars. I know I've got some initial kinetic energy. I'm going to make it kind of big because this boulder's rolling at me. I probably have some initial potential energy as well, since the boulder is partway up a hill. And then at the end of the day, I want there to not be any kinetic energy. So I'm going to make this bar 0. I'm just going to draw a really small blue bar for 0. And then I've got a potential energy, and it's going to roll down the hill. And I know that the potential energy gets larger, the gravitational potential energy gets larger the higher up I go. So I'm going to have less potential energy down here at the bottom. It doesn't necessarily have to be 0, right? I can imagine that there's a pit somewhere down here, right, that is even lower than where I am, right? And if the boulder were down here, maybe it would have 0 in it. I have total freedom. Okay, so I've drawn some energy bar diagrams. The first thing that I look at here is I see this and I say, uh-oh, the total energy of this system is changing, right? In particular, it's going down. The only way that that is going to happen is if I have done some work on the system. So I'm going to go over here. I'm going to add a bar here to represent the work done. This is going to be by me. And that is going to have to be pretty negative here, right? So I'm going to go ahead and draw a really big work bar that's negative. I don't know if that's the right size, but we'll go with it. All right. So now I've got an energy bar diagram. The last thing I want to do is get some symbolic things here, right? So I'm going to, again, split this up into initial and final. Initially, I've got some kinetic energy. So I'll write kinetic energy, initial, is equal to 1/2 mv squared, where I'm going to use a big M for the boulder. And then a V here, this is the initial velocity of the boulder, initial speed, so VI squared. And then I have some final kinetic energy, which I already said was 0. So KF is equal to 0. I also said that there was some potential energy here. So my initial potential energy is going to be, let's see, how do I want to keep track of this? I'm probably going to need to know something about where the boulder is. So let's go ahead and say that right there is the initial height of the boulder, HI. And then the final height is going to be when it's down here at the bottom. It's probably reasonable for me to say that that's at H equals 0, right? I don't have to, like I said, I could put 0 down lower, but I'm going to go ahead and put it there. And if I do that, I probably want to shrink these bars, right? Make it be that there's 0 potential energy here and maybe about that much potential at the top. So that means that this initial potential energy is just going to be the mass of the boulder, which is again big M, times little g times this H initial. And with this choice of where 0 is, I can actually say that the final potential energy is equal to 0. And now I can see that I've definitely drawn my work bar too big. I'm going to shrink it down a little bit, make it about that, a little bigger. So the last thing that I want to do on here is note that there's some work done here, right? So work done. This is going to be by me on the boulder. And if I assume that I can act a constant force on the boulder, then I could write this as my force, which I'll write as F normal, all right? That's probably a normal force, times the distance that the boulder moves. And the distance the boulder moves is actually this guy here, right? It is that distance there, which is not the same as H. In fact, you kind of need to do a little bit of trigonometry here. Looks like that distance is going to be HI divided by the sine of theta. So I'm going to do HI divided by the sine of theta here. It's the sine because that H side is the opposite side in the triangle that gets made there. Okay, so now I've got all of this. If I want to, I can put all this together into a conservation of energy, a work energy theorem expression, right? Which would say, and I'll switch to text here, Ki plus Ui, Kf minus Ki plus Uf minus Ui, that's the change in total energy of the system, is equal to the work net done by external forces, which in this case is the work done by. And there we have it. So we can plug all of these individual guys in here, all 5 of these guys in here, and we could solve for whichever thing we're interested in figuring out. Maybe how hard do I need to push on the boulder, or how fast could the boulder be going before I can't stop it, if I know how strong I am, for example. All right, hopefully that example was helpful. I'll see you in class.